You see Machu Picchu as an ancient ruin, a monument to a vanished civilization slowly crumbling. That's the smallest version of what it is. 60% of this city is invisible, buried underground, a drainage system still running at 85% efficiency after 500 years with zero maintenance. Its walls survive earthquakes by moving. Each stone shifts, absorbs the impact, and settles back. A water channel carved in 1450 still delivers drinkable spring water today. Machu Picchu isn't a ruin, it's a machine, still running. Built by hand at 2,530 meters, without a single iron tool, wheel, or crane, the entire city was constructed and abandoned in roughly 80 years, less time than the United States has existed, and it has been waiting completely intact ever since. Hit subscribe before we go deeper. This isn't information you stumble on twice. By the end, you'll understand why they hid it. Lock it in. Click now. The most unsettling thing about Machu Picchu is not what was built there. It is what was known there, by people working without written science, without metal, without wheels, and how completely that knowledge has disappeared. We are still reverse engineering decisions they made intuitively, still discovering infrastructure they buried so well it took radar to find it. The city didn't fall. It didn't burn. It was simply left. And in leaving, it became the most perfectly preserved window into a civilization that solved problems we are still struggling to understand. Here is the problem that engineers still cannot fully solve. Sometime around 1450 AD, a workforce of Quechua-speaking laborers, men who had never seen a steel chisel, never laid hands on an iron lever, never pushed a wheeled cart, built a functioning city on the spine of the Andes Mountains. Not a village, not a fortress, a city, with palaces, temples, aqueducts, astronomical observatories, and agricultural systems capable of feeding hundreds of permanent residents. They built it at 2,130 meters above sea level, on a narrow ridge between two mountain peaks, surrounded on three sides by near-vertical cliffs dropping into jungle river valleys. The man who ordered it was Pachacutec, the ninth Sapa Inca, supreme ruler of the Inca Empire. His name in Quechua means, "he who transforms the earth." Around 1438, after a decisive military victory over the rival Chanca people, Pachacutec began an aggressive territorial expansion that would grow the Inca Empire into the largest in pre-Columbian history. He didn't just want territory, he wanted something that would outlast him. He chose an impossible location and told his engineers to build. Official archaeology explains the workforce through the Emaita system, a form of civic labor duty where communities throughout the empire contributed workers to state projects in exchange for food, clothing, and prestige. This is well documented and almost certainly accurate, but Mitar explains who moved the stones. It does not explain how. The granite used for the most important structures was quarried from outcrops at the very edge of the ridge. Some of it transported more than a kilometer across steep, irregular terrain at altitude, without metal tools and without wheels. The Inca knew what a wheel was. Small ceramic wheels have been found on Inca children's toys. They chose not to use it, almost certainly because a wheel is functionally useless on Andean mountain terrain, where the ground is perpetually uneven, wet, and near vertical. Their solution was something more demanding: human coordination at massive scale, guided by engineering knowledge transmitted entirely through oral tradition and quipus. Knotted string records that encoded spatial and logistical instructions across generations of Quechua-speaking builders. In 2008, a team of engineering students from the Universidad Nacional de Ingeniería in Lima attempted to move a 2-metric-ton granite block 100 meters uphill, using only tools available to the Inca 40 volunteers. 4 hours. The block moved 11 meters before the wooden rollers cracked under the combined weight and gradient. 11 meters. The largest blocks at Machu Picchu weigh between 14 and 20 metric tons. The most detailed colonial account of how the Inca actually moved these stones comes from Pedro Chiesa de Leon, a Spanish soldier and chronicler who traveled through the empire between 1535 and 1550. He described massive fiber cables pulled by hundreds of men in coordinated rhythm, temporary earthen ramps constructed alongside building projects and dismantled once blocks were placed, and what he called moving stones with cunning, a phrase implying mechanical advantage beyond brute force that he either couldn't explain or didn't fully understand. Physical evidence supports parts of this account. At the upper quarry on the eastern edge of the ridge, researchers have found partially worked stones still connected to bedrock by thin fins of uncut granite, showing the extraction technique. Wooden wedges, driven into natural fracture lines, soaked with water to expand and split the block along a predetermined plane. Clusters of smooth, rounded river stones, found along likely transport routes, suggest primitive ball bearings placed beneath blocks to reduce friction. Experimental reconstructions using this technique have shown a 10-ton block can be moved by approximately 100 people, pulling in synchronized rhythm. The final placement remains the hardest problem to solve. Architect Jean-Pierre Protzen of the University of California, Berkeley, who spent years studying Inca construction, proposes an iterative fitting process. Place the block roughly, mark the high contact points, remove the block, grind down those points with abrasive stone, and repeat, potentially dozens of cycles over days or weeks, until the fit achieves the required precision. The result is stonework where a credit card cannot pass between joints, on blocks weighing tons placed at height. Without machinery, the city contains approximately 200 structures built this way. Modern construction engineers who have studied the site agree on one unsettling point. Given the location, the materials, and the absence of technology, the timeline of construction, estimated at 50 to 70 years, would be refused today as physically impossible. The Inca didn't refuse it. They climbed the mountain and began. But the visible stonework, as astonishing as it is, represents only part of the engineering achievement at Machu Picchu. Because the most brilliant decision the Inca made wasn't about the walls you can see. It was about what they buried 6 meters beneath your feet, and it is the reason the city is still standing at all. When tourists arrive at Machu Picchu, they look up, at the temples, the terraces, the twin peaks framing the skyline. Almost no one thinks about what is directly beneath their feet. That is exactly what the Inca intended, and it is exactly where their most consequential engineering decision was made. The ridge on which Machu Picchu sits is not a stable platform. It is a geological fault zone, laced with natural fractures, saturated by one of the most aggressive rainfall patterns in South America. The selva, the high jungle surrounding the site, receives up to 1,100 millimeters of rain per year. Tropical storms can dump several inches in a single afternoon. On a steep mountain ridge, that water has one natural direction, down, through the soil, loosening it, turning solid ground into a slow-motion river of mud. On a narrow ridge at 2,430 meters, that process produces catastrophic landslides. The Inca solved this before they placed a single visible stone. In 2000, engineer Ken Wright and archaeologist Alfredo Valencia Zagara conducted a systematic study of Machu Picchu's subsurface structure using ground-penetrating radar and careful excavation. What they found changed how engineers understand the site entirely. Approximately 60% of the total construction effort at Machu Picchu, by Wright's estimate, went into work no visitor would ever see. Beneath the city, the Inca had built a foundation system of extraordinary complexity. Descending layers of crushed white granite functioning as a biological filter, slowing rainfall, separating it from soil particles, redirecting it downward through 130 separate drainage channels, rather than allowing it to saturate the ground beneath the structures. Below those drainage layers, the Inca excavated to bedrock, sometimes 6 meters deep, and placed massive unshaped stones as ballast, lowering the ridge's center of gravity and reducing the tendency of saturated soil to slide. When the Getty Conservation Institute analyzed the drainage system in 2009, they found it operating at roughly 85% of original efficiency. 500 years old, zero maintenance, still working. But surviving tropical storms was only half the challenge. The Andes are one of the most seismically active mountain chains on Earth. For any ordinary stone building, regular major earthquakes mean eventual collapse. For Machu Picchu, they revealed something seismologists found almost impossible to believe. On May 21, 1950, a significant earthquake struck Cusco, 75 kilometers from Machu Picchu. Colonial Spanish buildings throughout the city, constructed with mortar and right-angle corners, collapsed in significant numbers. The Inca walls beneath those colonial buildings were untouched. The technique responsible is polygonal masonry, the fitting of irregularly shaped, multi-angled stone blocks without mortar, each one carved to interlock with its neighbors across multiple contact surfaces simultaneously. The blocks are not rectangles. They are complex polygons, some with as many as 12 distinct faces, each face carved to match the corresponding face of the adjacent stone. When an earthquake hits a wall built this way, the blocks don't break. They move. Each stone shifts microscopically, absorbs the wave, redistributes the energy across multiple contact surfaces, and settles back into its original position when the vibration passes. Engineers at Pontificia Universidad Católica del Perú who studied this behavior in laboratory simulations, described it as controlled micro-movement. The wall doesn't resist the earthquake, it dances with it. Two additional design choices made this system complete. First, Inca walls lean slightly inward, typically 3 to 5 degrees from vertical, creating a natural restoring force after any lateral displacement. When an earthquake pushes the wall outward, gravity pulls it back. Second, every doorway and window opening at Machu Picchu is trapezoidal, wider at the base than at the top. A rectangular opening concentrates stress at its right-angle corners during seismic movement. A trapezoidal opening distributes that stress downward and outward along diagonal edges away from the opening itself. Every doorway was engineered for earthquakes the builders knew were inevitable. Archaeologist John Rowe of the University of California, Berkeley, wrote in 1944 that Inca polygonal masonry was, in his assessment, unmatched by any pre-industrial construction tradition on Earth. Laser scanning analysis has since confirmed that contact surfaces between blocks achieve fits varying by less than 0.5 millimeters across areas of several square meters, achieved entirely by hand. With bronze tools, abrasive sand, and accumulated Quechua knowledge passed through generations, a city engineered to survive both its mountain and its sky. But surviving required more than foundations and earthquake-resistant walls. It required food, it required water, and obtaining both at 2,430 meters above sea level, on a ridge surrounded by cliff faces and jungle, demanded an agricultural and hydraulic system every bit as sophisticated as the stone above it. In the summer of 1997, a hydrological engineer named Kenneth Wright stood at the uppermost spring source above Machu Picchu and did something deceptively simple. He turned on a flow meter and measured the output of a small stone-lined channel carved into the mountainside roughly 500 years earlier. The channel was still intact, the spring was still flowing, and the water moving through that ancient carved channel was, by every standard of modern water quality testing, clean enough to drink. Wright had spent years studying Inca water systems, but standing there, watching 5 centuries of uninterrupted flow through a channel built by people who had never heard the word hydraulics, he later wrote that he experienced something he described as professional humility. The Inca hadn't just built a water delivery system. They had built one so precisely adapted to its environment that it was still outperforming many modern municipal systems in developing world cities. The system begins at a natural spring located approximately 750 meters north of the city on the slopes of Machu Picchu mountain. The Inca redirected its output through a primary stone channel descending toward the city at a gradient of precisely 3%. That gradient is not accidental. 3% is the minimum slope required to maintain continuous flow without stagnation, and the maximum slope at which water moves without eroding the channel walls. The Inca identified that optimal range through empirical observation and held to it across the entire 750-meter length, across terrain that varies considerably in natural gradient by making continuous micro-adjustments to the channel's carved depth. The primary channel feeds a cascade of 16 fountains distributed throughout the city in strict hierarchical sequence. The first fountain, positioned immediately at the channel's entry point into the urban core, was reserved exclusively for the Sapa Inca, or high priests conducting rituals in his name. The water then passed to the second fountain, reserved for the next rank of nobility, and so on down the cascade. The entire social hierarchy of the city was encoded in the sequence of water access. In Inca civilization, water was not simply a resource. It was a sacred substance, and its distribution was a political statement carved in stone. The agricultural terraces that surrounded this water infrastructure are equally sophisticated. Machu Picchu's famous andenes, the word derived directly from Quechua, are not simply flat planting surfaces cut into the hillside. Each terrace begins with a fitted stone retaining wall, behind which the Inca constructed a 4-layer system. Large stones as a drainage base, then gravel, then coarse sand, then imported topsoil, physically carried up the mountain from fertile valley floors below, because native mountain soil was too thin and too acidic for reliable crops. The entire sequence replicates the natural soil profile of a river-valley floodplain. The Inca were not farming on a mountain. They were recreating a valley on the mountain's face. The stone retaining walls also function as thermal buffers, absorbing solar heat during the day and releasing it at night, maintaining soil temperature several degrees above ambient air. This extended the effective growing season at Machu Picchu by an estimated 30 to 60 days per year. Archaeobotanical analysis of terrace soil samples conducted by researchers from the University of Florida in the early 2000s, identified evidence of maize, potatoes, quinoa, and various tubers, a diverse agricultural portfolio providing meaningful resilience against single-crop failures at altitude. Agronomist Gary Urton of Harvard University has estimated that the site's approximately 4.9 hectares of terraced agriculture could sustain between 550 and 750 permanent residents, year-round using Inca-intensive cultivation techniques. The city was self-sufficient, fed by its own engineered hillside, watered by a spring that has never run dry. When restoration teams began working at the site in the late 20th century, they found the primary water channel structurally intact after 500 years of abandonment. The drainage layers beneath the terraces were functioning exactly as designed with zero maintenance in one of the most aggressive rainfall environments in South America. But sustaining the body was only half of what Machu Picchu was built to do. Because this city was not built primarily as a residence or an agricultural station, it was built as a sacred space, where the movements of the sun, the positions of the stars, and the geometry of the mountain itself were integrated into every stone, every alignment, every shadow that fell at precisely the right moment, on precisely the right surface. Understanding that dimension requires looking past the terraces and fountains to the highest point of the urban core, and the stone standing there, waiting for the solstice. On June 21st every year, at the precise moment of the winter solstice in the southern hemisphere, something happens at Machu Picchu that has happened every year for approximately 575 years. The rising sun clears the horizon at a specific point between two mountain peaks to the northeast. Its light travels in a direct line across the central plaza, enters the Temple of the Sun through a specific trapezoidal window on the building's curved eastern wall, and falls in a perfect rectangle of light onto a carved granite outcrop at the temple's center. The rectangle holds its shape for approximately 4 minutes. Then the sun moves, the light shifts, and the alignment is gone for another year. This is not coincidence. The Temple of the Sun, called Torreon by Spanish chroniclers, was oriented by its builders to within a fraction of a degree of the precise solar azimuth of the June solstice sunrise at this specific latitude and altitude. Its curved wall, unique among all structures at Machu Picchu, where every other major building has straight walls, was built in that shape specifically to track the sun's arc across the sky throughout the year, allowing the angle of incoming light to be read like a dial across the curved surface. The astronomical knowledge behind this system was accumulated by Quechua-speaking skywatchers across generations, sophisticated enough to track not just solstices, but equinoxes, lunar cycles, and the rising positions of specific star clusters. The Pleiades held particular importance, their heliacal rising, the moment they first become visible above the horizon before dawn, determined planting calendars across the empire. Several alignments at Machu Picchu, including specific window orientations in the Torreon and the angles of certain terrace walls, appear calibrated to the Pleiades' rising position at this latitude. What is not debated is the Intihuatana. The word means, in Quechua, hitching post of the sun. It is a carved stone pillar rising approximately 60 centimeters from a larger granite platform at the highest point of the urban core. It is the only one of its kind to survive intact anywhere in the Inca world. When the Spanish conquered the empire, they systematically destroyed every Intihuatana they found, recognizing these stones as objects of supreme religious devotion and targeting them specifically as part of their campaign to dismantle indigenous spiritual practice. The one at Machu Picchu survived because the Spanish never found the city. Archaeoastronomers Brian Bauer and David Dearborn, in their 1995 analysis, confirmed the Intihuatana functioned as a solar gnomon, a precisely carved shadow-casting instrument, tracking the sun's position throughout the year with enough accuracy to serve as both agricultural and ceremonial calendar. At the two equinoxes, the sun stands almost directly above the pillar at midday, casting virtually no shadow. The Inca interpreted this as the sun sitting on its hitching post, one of the most sacred moments in their ceremonial calendar, marked by empire-wide festivals and rituals. Architect Johann Reinhard, who has spent decades studying Inca sacred geography, argues the pillar simultaneously pointed toward the 4 sacred peaks surrounding Machu Picchu in the cardinal directions of the Inca cosmological system, the 4 Suyus, the regions dividing the empire. The Intihuatana was not simply a calendar, it was a compass, a ritual instrument, and a physical axis connecting the city to the empire's sacred geography simultaneously. The broader urban plan encodes this cosmological thinking at every scale. The city is divided into Hanan, Upper District, and Hurin, Lower District, mirroring the sacred organizational duality of Cusco itself. Machu Picchu was not simply built in the mountains. It was built as a physical model of the Inca universe, a map of cosmic order rendered in granite and skyline alignments. Astronomer Anthony Aveni of Colgate University has noted that what distinguishes Inca astronomical practice from other ancient traditions is its integration with landscape rather than separation from it. While Greek and Babylonian astronomers built instruments to observe the sky in abstraction from their surroundings, Inca astronomers used the mountains themselves, their peaks, their shadows, their skyline silhouettes, as the instruments. Machu Picchu, positioned with specific mountain peaks visible at specific azimuths in every direction, was not a city with an observatory attached to it. The entire city was the observatory. Pachacutec didn't choose this ridge arbitrarily. The mountains, the solar alignments, the sacred spring, all of it was already holy in Inca cosmology before the first stone was laid. The city was built to inhabit a place the sun itself had marked, which makes what happened next all the more haunting. Because the man who showed this sacred city to the modern world wasn't looking for it at all. He was looking for something else entirely, and what he stumbled onto instead would become the most famous archaeological discovery of the 20th century, hidden in plain sight above a river valley that local farmers had never stopped visiting. On the morning of July 24, 1911, a 35-year-old Yale University lecturer named Hiram Bingham III was riding a mule along the banks of the Urubamba River when a local farmer named Melchior Arteaga offered, for the equivalent of a few coins, to show him some ruins on the ridge above. Bingham was cold. It was raining. His traveling companions declined to make the climb. He went anyway, hauling himself up a near vertical jungle slope for 2 hours by tree roots and vine handholds. At the top, he found a local family, the Richart family, later documented by archaeologist Paul Fayos in the 1940s, living among the ruins, using the ancient terraces to grow vegetables. They had been there for years. They knew exactly what the stone structures around them were. They simply hadn't told anyone who was writing things down. This detail dismantles the most persistent myth surrounding Machu Picchu's discovery, the image of a lost city swallowed entirely by jungle, invisible and forgotten, waiting for a Western explorer to rescue it from obscurity. Local Quechua-speaking communities had maintained continuous knowledge of the ruins. A German engineer named Augusto Burns had visited in the 1860s. A British missionary noted the location in the 1870s, none of them published. What Bingham did, and what separates his expedition from all earlier contacts, was document, photograph, and tell the world. National Geographic devoted its entire April 1913 issue to the discovery, introducing Machu Picchu to millions of readers simultaneously. The irony Bingham himself acknowledged in his later writings: he had not been looking for Machu Picchu. He had been searching for Vilcabamba, the legendary last refuge of the Inca Empire, where the final rulers retreated after the Spanish conquest and resisted colonial rule until 1572. The actual site of Vilcabamba was identified decades later at a different location entirely, a place called Espiritu Pampa, deeper in the jungle to the northwest. The reason Machu Picchu survived where every other major Inca site was found and stripped was geographical and political simultaneously. The Spanish conquistadors who dismantled Cusco's Golden Coricancha temple demolished Inca palaces to build colonial churches on their foundations and systematically destroyed every Intihuatana they encountered, never found this ridge. The city does not appear by name in any Spanish colonial record from the conquest period. Historian Richard Berger of Yale argues the most likely explanation is that the city's population had already collapsed before Spanish soldiers arrived, devastated by the smallpox epidemic that swept the empire beginning around 1527, killing an estimated 65 to 90% of some regional populations before a single conquistador crossed into Inca territory. If Machu Picchu was already largely abandoned by 1532, there was no one left to interrogate about its location. The selva did the rest. In a region receiving 1/900 millimeters of annual rainfall, vegetation can completely obscure a stone structure within decades. Within a century of abandonment, the city was invisible from below. But this raises the deeper question: why was the city abandoned in the first place? Machu Picchu was built around 1450. The Spanish arrived in 1532. That is roughly 80 years of occupation, possibly less. For a city constructed with this level of investment, this degree of sacred significance, this precision of engineering, 80 years is not a lifespan. It is barely an introduction. Archaeologist Richard Berger, after decades of study, identifies the smallpox epidemic as the primary cause, not just of the city's abandonment, but of the entire chain of events that followed. The epidemic killed the Sapa Inca Huayna Capac around 1527, triggering a catastrophic civil war between his two sons, Huascar and Atahualpa, that fractured the empire's administrative and military cohesion precisely when the Spanish arrived. Machu Picchu, as a royal estate tied to Pachacutec's specific lineage, lost its political and ceremonial function as the empire collapsed around it. With no court to serve, no pilgrims traveling the roads, and a population already decimated by disease, the city was not destroyed or conquered. It was simply no longer needed. People left. The jungle moved in. And for 400 years, the mountain kept its secret. What Machu Picchu forces us to confront is not simply the achievement of a vanished civilization. It is the fragility of knowledge itself. The Quechua engineers who designed that drainage system, who calibrated that water channel to a 3% gradient by hand, who understood intuitively how granite responds to seismic waves, none of them wrote it down. It lived in hands, in practice, in the oral traditions of communities that were then decimated by disease and conquest. And when those communities collapsed, the knowledge collapsed with them. We didn't inherit their understanding. We inherited their stonework. And we are still, 500 years later, working backward from the stones to figure out what they knew. Researchers continue to study the site with technologies its builders never imagined: ground-penetrating radar, laser scanning, archaeobotanical analysis. And with every new investigation, the scientific community finds something that current models of pre-industrial capability cannot fully explain. These are not conspiracy theories. They are open questions in mainstream archaeology and engineering. The ongoing research reminds us that history is still being written, that what we call primitive and what we call advanced are categories that the evidence at Machu Picchu quietly refuses to respect. The deeper question this city asks is personal. Pachacutec built something intended to outlast him by centuries. It has now outlasted his entire civilization. What knowledge are we failing to preserve right now? Encoded in practice, in tradition, in ways of understanding the world that we are allowing to disappear. Every generation assumes it is the most sophisticated. Every generation leaves ruins that make the next one wonder. Scientists and archaeologists are still working to explain what was built on that ridge. The stones are still dancing, the water is still running, and the mountain is still keeping secrets.